Um, Thank you very much for joining this evening's presentation once again. Brian can't be with us this evening, but I know if he were able to join us, he'd want to express his thanks not only to Projex Solutions, but also to the IMechE West Yorkshire and the University of Huddersfield, who've been instrumental in putting together this series of lectures and presentations. My name's Dan Wells. I'm the National Consultant Specialist for Spirax Sarco UK and Ireland. I've introduced Spirax Sarco on a number of occasions now, so hopefully during this series of presentations you've got a good feel for who we are as an organisation. Simply put, we're a global entity, we're a British company, FTSE 100 listed, and we operate across 3 different business streams. I personally work for the Steam Specialties division, but sitting alongside our Steam Thermal Solutions division, we have our Electric Thermal Solutions team that manufacture a number of interesting innovations that can essentially help our steam using clients move away from natural gas and instead generate steam from electricity, whether that be grid electricity or renewable electricity. And more recently, we've heavily invested in different technologies such as thermal energy storage in the form of molten salt and also high pressure, high temperature heat pumps. We'll talk about those in a little bit more detail in the presentation that we have next week, which is the last of this series of 8. And of course, I've also introduced Spirax Sarco in the UK and Ireland in some detail. Please do check out that series of resources that we have on our website. And please also remember those 2 different calculators and configurators that we have that are particularly useful for design engineers. First of all, as the basis of design, because if we understand how much heat energy our client's process requires, by nature, we've calculated the mass of steam that's required, and from then on, we've calculated the size of the heat exchanger, the control valve, the steam trap, the steam pipework, and also the condensate pipework. But as far as today's presentation is concerned in particular, we also remember that those calculators and configurators are instrumental in helping us calculate our cost of steam. It really is the very, very first question that we need to ask whenever we're engaging with a steam system. What's the cost of steam? How much does it cost to produce a ton of steam? A lot of our clients won't be aware of that information. And those that are aware may be basing it on outdated information. So in order to correctly understand our cost of steam, we need to understand the cost of gas. That's the big one. And that's changed significantly over the last 4 to 5 years. So if we're basing our cost of steam on outdated information, then we could be way off the mark. Cost of gas. We then need to understand the cost of water. And of course, that's going to vary from one part of the country to another. And we may not necessarily be using water from the mains. We could be using borehole water, river water, reclaimed water. That's going to vary. We're then going to have to chemically condition that water to make it suitable for the boiler. We then need to take into account the pressure and temperature that the boiler operates at. And we also need to give thought to the combustion efficiency of the burner that furnishes the boiler. That's going to vary, probably somewhere between 82 and maybe 86%. But the biggest piece of information of all is the temperature of the water that goes into that boiler. If we know all of those variables, we can calculate our cost of steam. And that's important because if we're able to engineer, if we're able to optimize and improve the steam generation, steam distribution, the steam trapping, the condensate return, how we use the steam at the process, if we're able to make incremental step changes to reduce the mass of steam that is used and to reduce those distribution losses, well, simply put, the boiler doesn't have to work as hard. We're not consuming as much gas. And by nature, those carbon emissions are also going to be significantly decreased. Simply put, we can only have an understanding or measure that information if we've calculated the cost of steam to start. So, as we've mentioned, we've gone through a series of presentations to date. We started off back in September when we met at the university and we looked at the basic principles of steam fundamentals. We moved forward and we looked at the best practice that we need to employ to move the steam from the point of generation to the point of use. We looked at steam trapping, one of the most important individual ancillaries on a steam system. We looked at the fundamentals of heat exchange. We then moved on to look at how and why it's critically important to recover as much of the condensate as we can. And last week, we looked at the concept of steam contamination, particularly important whenever we're using steam in critical environments, such as for food, beverage, pharmaceutical applications, where the steam can come into contact with a product or atmosphere. So today I want to move forward and I really want to explore the topic of energy efficiency in a little bit more detail. We know that it's going to be of particular interest to our client if we can help them reduce their cost of gas. But it's also going to be of particular benefit to them if by nature we can help them reduce their carbon emissions. So in today's presentation, we're really going to look at the quick wins that we can employ to optimize or improve an existing steam system. So one of the first things that we need to remember is whenever we're engaging with our client's steam system, that steam system could have been engineered 20, 30, or even more years ago. So it could have been engineered at a time when the cost of gas, the cost of water, the cost of steam was relatively cheap, where we'd never heard of carbon emissions, and where we lived with the inefficiencies that may exist within the steam system. Sure, we might be aware of different areas where we can optimize and improve that efficiency, but the payback may not have been too attractive at that time. So we lived with that inefficiency. But fast forward 25, 30 years, and the cost of steam, the cost of gas, and those carbon emissions are creeping up on us over time. They're unwanted. So we're really going to look in some detail with regards to where those inefficiencies may exist. Well, we know that there are a lot of different technologies out there to produce thermal energy for different processes. Spirax Sarco ourselves, we manufacture a number of different technologies, such as those steam heat pumps, steam batteries. We can electrify steam boilers. We're going to discuss that in some considerable detail in the next presentation in the series next week, but it's absolutely the wrong thing to do for our client to transition towards those new technologies today. There's some legwork that needs to go in before then. For example, the three-step approach that you can see on the screen, it really emphasizes the fact that the vast majority of those traditional steam systems that were engineered 25, 30 years ago, they're going to have a significant number of inefficiencies. So the first thing we need to do is really understand how efficiently or how inefficiently our client's steam system is operating. And from then on, we can understand the significant benefit we can bring to our client by addressing those immediate inefficiencies. For example, our client's boiler could be producing 10,000 kilograms of steam per hour today. But the processors may actually only require 7,000 kilograms of steam. So if we can reduce the capacity of the boiler, or if we can reduce the mass of steam that the boiler needs to produce from 10,000 to 7,500, then we've already made a significant leap forward in reducing our cost of steam, our cost of gas, and reducing those carbon emissions. So that's really is the first link in the chain, the first step that we're going to explore in some detail today. It's the optimise piece. We need to understand how and where those inefficiencies exist in an existing traditional steam system and understand what the payback, what the benefit is going to be if we can instigate those improvements. So, as we've mentioned, as steam engineers, we've got a reasonably good understanding where those inefficiencies are going to exist. So, as far as today's presentation is concerned, please think of the concepts that we're going to cover off. Please think of these as the quick wins. It may well be that our steam using client is already applying some of this best practice, but these really are the things that we need to check for even before we want to discuss or consider moving forward to apply those new technologies. So I've gone through the steam tables in some considerable detail in my previous presentations. I did warn you some weeks ago that I would go through this one slide in some detail on numerous occasions. So apologies for that. But what we need to remember is the steam tables, as fantastic a resource as they are, they only apply when the steam is 100% dry. And as we've mentioned in previous presentations, the drier the steam, the more energy there is contained within it. So if there's more energy contained within dry steam, the boiler doesn't have to work as hard, we're not producing as much gas, and of course, those carbon emissions are going to be kept to a minimum. So keeping the steam dry is fundamentally important for efficiency purposes. But the steam tables also tell us that there's some value retained within that condensate, for the simple reason that when steam gives up its heat energy and condenses, it gives up its energy, but it doesn't cool down. So as far as the heat exchange is concerned, as far as the infrastructure is concerned, that condensate is unwanted. It's a byproduct. We need to get it away so that we don't contribute to that inefficiency, but also so we don't get mechanical damage through an excess of erosion, corrosion, and water hammer. But the box in orange, it really emphasizes that if we can recover the energy that is present within the condensate and get it back to the energy center, then we've got a really, really good head start in helping the boiler to react quickly and efficiently to produce the steam that is required. So there's a benefit in getting the condensate away, and there's a benefit in returning the condensate as well. We need to keep that in mind whenever we're moving forward to explore the areas for efficiency improvement. So we've also mentioned the pressure temperature and the pressure volume relationship in some detail. Now, in previous presentations that we went through, we mentioned the purpose, the reason for those steam vents. For the simple reason that if one of those steam traps were to fail, we're going to have high pressure, small volume steam depressurizing and expanding. But we're also going to have high temperature, high pressure condensate depressurizing. And of course, when that happens, a certain mass, a certain percentage, it's going to want to boil off and expand and change state to steam again. So of course, we're going to have to vent that expansion away so we don't get damage to the infrastructure. The problem is it's a necessary evil. We've got to vent that expansion away, but whilst those steam vents are left unchecked, it essentially means that the boiler's working harder and harder to replace that missing steam. So we've got more steam going into the sky, and of course, we now no longer have that opportunity to recover and return the condensate. So our cost of steam, cost of gas, and our carbon emissions are going to increase significantly. So even before we move to look at the areas for optimizing and improving efficiency, we really need to take note of the information that's staring at us in the face. Those vents are telling us that there is a significant inherent inefficiency that needs to be addressed immediately. Okay, so I'm going to start off by visiting the boiler house, steam generation. So as we've mentioned in previous presentations, our client is likely to have anywhere between 2 and 6 of those horizontal fire tube steam boilers. Typically, they're going to be operating at a pressure somewhere between 7 and 12 bar gauge. And we can then be distributing that steam thousands of meters around site to supply the heat energy for the various processes. So the best means of generating the best condition, the driest steam that we can, it really means that we need to look at how we're operating the controls of the boiler itself. So we've mentioned previously the benefits of generating steam in a high pressure boiler. High pressure boiler, temperature. High pressure, small volume, small infrastructure, a lot of motive energy to move it around site. Typically, at a higher pressure, we get a better quality, in other words, drier steam with more energy present within it. And it also means that we get a smaller infrastructure, a smaller boiler itself. So, bearing that in mind, the next thing that we want to look at is ensuring that we've got a meter for each individual steam boiler, or at the very least 1 meter per boiler house, because it's only by metering the mass of steam that is being produced that we can really say with any real confidence that we understand what our cost of steam is. And then if we're metering the steam that is leaving the boiler house, and we're metering the steam as it arrives at each individual building or heat exchanger, well, that way we can understand how much steam is going missing in the middle. And that could be down to having excessively wet steam that's condensing out in the pipes, or it could be down to the fact that we've got failed steam traps. But it's only by measuring the steam, metering the steam, that we can have confidence in where those efficiencies may lie. And if we were to repair or rectify those inefficiencies, we're going to want to have an understanding on what the payback is, what the benefit is, how much steam we've saved, how much gas we've saved, and the extent at which we've now reduced those carbon emissions. We can only prove that if we're metering. So moving forwards, one of the next quick wins is ensuring that we've got high temperature hot water that is there on demand for whenever the steam boiler needs to respond and produce steam. We need to keep that hot well at a nice high temperature. Ideally, around about 85 degrees. We can't hold it at a higher temperature for reasons we've mentioned in those previous presentations. It's down to the fact that if we've got hot water at a temperature that is way in excess of 85 degrees, we're likely to get cavitation and failure of electrical components such as the boiler feed pumps. High temperature hot water is self-explanatory. It means that we don't need to consume anywhere near as much gas in order to bring that water up to the point where we're producing steam again. Now, there's a very quick rule of thumb for you here, and that's that if we're able to elevate the temperature of the water in storage by 6 degrees up to a maximum of 85 degrees, we expect to see a cost saving on our fuel of 1% straight away. It's a very, very quick win. How do we keep the hot well at a nice high temperature? We recover as much of that hot condensate as we possibly can. Level controls are also an interesting one. The biggest purpose of the level controls is to ensure that the water level doesn't fall to a dangerously low point where we could have a catastrophic incident. So it needs to be capable of sending a signal to a burner to shut off the steam production. The other purpose is, well, if we think of a steam boiler, think of it as being a can of Coke. It's a horizontal vessel. So if we fill that can of Coke 75% full, we lie it on its side, well, we know exactly where the water surface area is. And when we know the pressure of the boiler, we've got an understanding of the velocity of steam that is leaving the boiler. Now, if that water level were to rise to a very high point or fall to a very low point, the surface area is going to change. And that means the steam velocity can leave the boiler at a much greater speed than we're expecting. That can drag a lot of water out of the boiler that's really going to contribute to that wet steam that we're desperately trying to avoid. Remember, wet steam means we're going to get a lot of erosion of different ancillaries, but there's also less energy in wet steam. And because wet steam is far more likely to condense out in the pipework, means we're going to get a higher condensing load and a further inefficiency. Now, we need to remember that there are only certain types of level controls that can hold an accurate and reliable level within the boiler. And that's a capacitance probe. A capacitance probe, for example, that can send a signal to a modulating pump, which means we can hold the level of the water within the boiler at an accurate and defined point, meaning that the water coming into the boiler is going to be in equilibrium with the steam that is leaving the boiler. It means we're getting a much, much better condition of steam, far, far drier, with more energy present within it. And it's actually the level controls themselves that send the signal to that modulating pump. Fortunately, the level controls and the modulating pumps, they can be retro-engineered. So we can improve the condition, or we can improve the sophistication and efficiency of those controls, but leave the original boiler intact. So those modulating feed pumps that we spoke about, another benefit is if you compare a modulating feed pump to an on-off pump, it means that with an on-off pump, the level control may have been set at a very high point for switching off and at a very low point for switching on. We could be bringing a significant mass of water from the hot well in a very short period of time. And if the water in storage in the hot well was at a relatively low temperature, we're going to have a quenching effect. So there's going to be a delay to the point at which we can produce steam. And it also means the ability of the boiler to produce the required mass of steam is going to be further diminished. So if we've got one modulating feed pump in the boiler house supplying 6 boilers, we can be pumping a small mass of very, very high temperature hot water. Whereas if we had an on-off system, then we would require 1 pump per boiler. And that'd have a greater demand of energy and also a burden of maintenance. The blowdown, we've looked at the blowdown in some detail in previous presentations. Blowdown is the means of maintaining the correct water chemistry within the boiler. So we want to perform what we call bottom blowdown to ensure that that heavy particulate is adequately flushed away. Now, many of our clients, they may be blowing down from the boiler with a manual valve. So if we've got water in storage at 10 bar gauge, 184 degrees, whenever we open that valve, the extent of that high temperature hot water depressurizing as it moves across the valve, that's going to have a benefit because it's helping to flush the particulate away. But unfortunately, for every kilogram of hot water we put to waste at 184 degrees, we've got to replace it with the same mass of what could potentially be significantly colder water. So of course, we've got an energy inefficiency. Unfortunately, with bottom blowdown, there's no opportunity for heat recovery. It's got to go straight to the bottom blowdown vessel with no hindrance there. But what we could perhaps look at doing is moving away from a manual blowdown valve to an automated bottom blowdown valve. If we've got a timer on the actuator, then by understanding the size of the valve, the pressure of the boiler, the number of seconds it's in the fully open position for, then we're able to have a good understanding of the mass of hot water that's being flushed to waste, and therefore the efficiency versus inefficiency. All we can really hope for is to keep that mass of hot water that's dumped to waste to an absolute minimum. And then we spoke about the TDS blowdown, remembering that TDS stands for total dissolved solids. Some of those chemicals and minerals, they're never going to solidify. They're always going to be held in suspension. But if that TDS level is allowed to rise to a high concentration, we're more likely to get foaming within the boiler itself. And a fluctuation in boiler pressures, that means that that foam can be drawn out of the boiler along with the steam, and that's really going to contribute to that wet, sticky steam that we're desperately trying to avoid. Not only is the steam going to have very little energy contained within it, but it also means that we're going to get more of the foam solidifying and changing state to scale. That scale can result in quite a bit of erosion of sensitive ancillaries, but that scale can also bind itself to heat transfer surface areas, meaning we've got a further barrier to heat exchange and a further inefficiency. So wherever possible, we want to ensure that we're monitoring the concentration of the TDS within the boiler constantly. it needs to be automated. So by having an automated TDS conductivity probe sending a signal to the modulating valve, it means that we can bleed out the required mass of hot water to waste and no more. If we're blowing down too much, we've got a very large inefficiency, but if we're not blowing down enough, we're going to get contaminated steam. So as with the bottom blow down, if we automate that, and if we automate the TDS blowdown, it's vitally important to make sure that it's routinely serviced and calibrated so those values don't drift. Now, we can't recover any of the heat energy from the bottom blowdown because best practice says that that needs to go straight to the blowdown vessel itself. But with the TDS blowdown, we can. This has got a very attractive payback. It's something that's quite often overlooked because in years gone by, when the energy centre was engineered, the cost of gas, the cost of steam was relatively low. Carbon emissions were misunderstood. Whereas today, we know that if we're able to recover as much of the heat energy from the boiler that's leaving from the water that's leaving the boiler and put it into another process, such as the hot well, then we appreciate the beneficial effect that can have in reducing the massive steam that the boiler needs to produce, and therefore help us to reduce our cost of gas and reduce those carbon emissions. So they're the quick wins when it comes to understanding how we can reduce the gas, the carbon emissions in the boiler house itself. But we also appreciate that we then need to move the steam a considerable distance around site. So if we're moving the steam at 10 bar gauge, 184 degrees, if we're moving it in a carbon steel infrastructure with missing, damaged insulation, one big radiator, we're going to get a significant amount of heat loss as the steam condenses in the pipe. We could be putting 10,000 kilograms of steam into the pipe. We certainly won't be getting 10,000 kilograms of steam out of the other end. So one of the best things that we need to understand is the benefit of not only generating a high pressure steam, it's in distributing a high pressure steam as well. Simply put, high pressure steam with a small volume, yeah, it's going to help us keep the infrastructure small, but it also means that we can help reduce the size of the pipework, which means we've reduced the mass of that radiator. We've reduced the heat loss. So we don't need as many steam traps to remove the condensate. We're going to get more steam finding its way to the process. We've got drier steam, so there's more energy in the steam, so the boiler doesn't have to work harder. So one of the most important things we can do is apply that best practice in order to ensure that the condensate can move out of the infrastructure very, very quickly. We don't want that condensate to sit there for too long, because by doing so, we're encouraging the mechanical issues like that erosion, the corrosion, the water hammer. But the steam's going to degrade, and as it degrades, it's going to have less energy contained within it. And as it gets wetter, it's more likely to condense, thereby reducing the mass of steam that's going to be available for the process. Insulation's another very, very quick win. Again, something that may have been overlooked 20, 30 years ago because it wouldn't necessarily have had the payback that we were expecting. But of course, today we appreciate the cost of gas, the cost of water, the cost of chemically conditioning the water. And we appreciate that by reducing the mass of steam that the boiler needs to produce, we're also reducing those carbon emissions significantly. So if we know the variables, the pressure, the temperature, the ambient conditions, the mass of steam, the size of the pipe, for example, then we can very often provide a significant payback for different ancillaries like traps or valves just by having an upgraded insulation jacket. And that information can be provided in terms of carbon saving, in terms of energy saving, or in terms of payback. So we've mentioned those steam traps. We need to ensure that we've engineered the correct type and the correct size of steam trap to get the condensate away from the distribution pipework. It's going to be a relatively small mass, but it's going to exist at a high temperature and therefore at a high pressure, which means it does have a value if we can get as much of that condensate, not only out of the infrastructure, but back to the boiler house where we can reuse it as well. So keeping those steam traps in mind to ensure that they're sized and selected correctly is critical. Drying the steam. As we've mentioned, dry steam is more likely to create a problem with erosion of control valves or of flow meters, for example. But it also means if we've got very, very wet steam, it means there's less energy present within the steam and therefore the boiler has to work harder. So ensuring that those separators are installed correctly is vitally important. They're quite often engineered out of steam systems when it comes to looking for areas where we can save a few pounds on the installation, but they're vitally important when it comes to understanding where that inefficiency may exist. So just to emphasize that point, the steam tables, we've mentioned previously that the steam tables only really apply when we understand that we've got 100% dry saturated steam, which sits on the red line that you can see here. So if we've got steam that is, I mean, this is an extreme example, but if we've got steam that is 50% dry, 50% wet, you can see we've got 50% of the expected energy present within it. So you can appreciate the extent at which the boiler would now have to work significantly harder in order to satisfy the requirements of our various heat exchangers. And of course, if not only we've got very, very wet steam, but if we've got a lot of air entrained within the steam as well, then because of the insulating barrier that film of air is going to have, then simply put, all bets are off. We know that we're going to have a significant inefficiency at the point of heat transfer. So the boiler is going to have to work all that more harder in order to satisfy the requirements of the heat exchanger. So we know the benefits of generating steam at a high pressure and distributing the steam at a high pressure. We've mentioned the benefits of then reducing that pressure as low as we can. Now, by generating and distributing at high pressure and then reducing the pressure, yes, it means we're protecting the capital equipment from overpressure, and it means we can move the steam very, very quickly in a small infrastructure. But we also know that there's actually more useful heat energy present within steam at a lower pressure than there is at a higher pressure. So we've got a significant benefit there for heat exchange purposes. So we need to bear that in mind when we get the steam to the point of use. So things to bear in mind when we're looking at how we use steam at the point of use, areas for optimization. Some of those critical applications, temperature sensitive applications, they will be controlled with an actuated control valve. It could be pneumatically or electrically actuated. Very, very sensitive, very, very smooth, sensitive surface areas. Typically, they're going to be metal to metal seated valves. And quite often we come across problems with control valves whereby they're oversized. So if we're moving steam in the pipework at a very high velocity, 40 meters per second, 90 miles an hour, as the steam moves across the control valve, if that control valve's modulating closed and operating very, very close to its seats, the speed of the steam can increase tenfold. So the steam can be moving across the control valve at maybe 350, 400 meters a second. That's not far off the speed of sound. You can appreciate that any moisture, any rust, any scale is going to create significant problems to the control valve, resulting in a lot of damage, a high cost of ownership. But ultimately, it's going to affect the process because we're going to have steam moving onto the heat exchanger when it's not required. So another rule of thumb for you here, when a control valve is correctly sized and correctly designed, we would expect that control valve to be sized approximately 2 pipe diameters smaller than the upstream connecting steam pipe. Better still if we've gone back to first principles and calculated the correct size of control valve. And also it tells us how and why those steam separators are critically important. So I want to give you an example here of how a control valve that's failing can create a problem. If we've got a control valve that's oversized and operating very, very close to its seat, then we expect a little bit of erosion. So if we've got a low pressure, low temperature application, it could be a frost coil on an air handling unit, for example. Any steam that is passing on to the frost coil and condensing, it could potentially result in a problem with that steam flooding the frost coil, or the condensate, should I say, flooding the frost coil. And if it were to remain there, then that condensate is going to freeze. And it's going to create quite an expensive failure of that frost coil. So rather than have one of those traditional metal to metal class 4 control valves, as we call them, we could potentially move forward to a class 6 peak seat control valve. It's a high temperature polymer, and that actually gives us an excellent shutoff rate. In fact, it's impossible to measure the benefit in shutoff rate in terms of percentage. It's literally down to a few bubbles of air that would be leaking across a control valve under laboratory conditions. So we're moving towards a position where we could potentially consider that control valve as an isolation valve as well, meaning we're less likely to experience erosion, and meaning we're protecting that frost coil from any unnecessary energy loss, but most importantly from any damage. And we also know that we may potentially come across issues in control valves if we've got a high pressure downstream of the trap. That back pressure may mean that there's insufficient pressure within the body of the frost coil itself in order to pressurize the condensate and move it across a trap. In many cases, it's going to be beneficial if we remove the trap altogether and move towards what we call an APT, an automatic pump trap. As we've mentioned in previous presentations, an automatic pump trap, it can remove the condensate regardless of the pressure conditions by simply borrowing a little bit of upstream motive energy from the steam in order to help drain that condensate away. Okay, so we looked at the topic of heat exchangers some weeks ago now. I just really wanted to loop back to this topic because there are going to be significant energy improvement benefits if we can move away from the issue of holding hot water in storage and instead moving towards a heat exchange solution that is generating hot water from steam instantaneously and on demand. Benefits, well, we don't have the issue of an inefficiency through the overproduction of too much hot water that's never likely to be used. We've minimized the risk of that energy loss through the hot water radiating its energy whilst it's held in the plant room. And the other reason is, if we're using a plate heat exchanger to generate hot water, it means that we've got a much bigger heat transfer surface area, as we can see on the image towards the right hand side of the screen, which in turn means we can condense the steam at a lower pressure and lower temperature, which, as we've already mentioned, means the steam's got far, far more energy in it, and therefore the boiler doesn't have to work as hard. So, of course, wherever we're using steam for heat exchange purposes, we need to remove the condensate. We're going to be removing a much greater mass of condensate than the condensate that exists in the distribution pipework. But that condensate is going to exist at a lower pressure and lower temperature. But it's still vitally important that we need to get the condensate away. But it really reminds us that we're going to need a completely different size and a completely different type of steam trap in order to fulfill that purpose. The problem is, and it doesn't matter what type of steam trap we're talking about or where it's located, steam traps, they are mechanical devices and they can and they will fail. especially if those steam traps have been, if it's the wrong type of steam trap selected, if it's been sized incorrectly, installed incorrectly, if it's been failed to be maintained, it will fail. Another rule of thumb, we'd probably expect a 1 in 10 failure rate. And that assumes that we've got a good quality of steam and that the steam trap has been engineered correctly. So if our client had 100 steam traps on site, we'd expect 10 of them to be in the failed position at any one time. So over towards the right hand side of the screen, you can see what the implication is. It means that we're going to have a visible plume of steam venting away until such a time that they can be repaired. And every steam trap type has got approximately the same orifice size. So if we know the trap type, size, if we know the steam pressure, we know approximately how much energy is being lost whilst that trap is left to remain in the fully open position. So we can quantify what that energy loss looks like, either in terms of energy, or if we've taken that further step and calculated our cost of steam, we can then understand what that single trap is contributing to in financial loss over a 12-month period or until such time it's repaired or replaced. And remember, we could have multiple traps on site that are failing. So it reminds us why steam trap engineering is one of the biggest and one of the quickest wins when it comes to ensuring that our steam system is operating efficiently. And it also reminds us why our client is going to want that periodic steam trap survey in order to ensure that those traps have been correctly installed, engineered, maintained, that they're not failed, that they're selected correctly. And in certain applications, our client may wish to move towards some form of automation to instantly understand if and when that trap has started to move towards a failed condition. So we've mentioned that condensate does have a value. That's why we need those steam traps. And the condensate is essentially going to exist wherever there is heat loss. So that can be in the pipework itself, or it can be at the processors. There is still a value. And we know that the steam tables tell us there's approximately 25% of the total heat energy of the steam is retained within that liquid condensate. So it reminds us that if we've calculated our cost of steam correctly, we can understand the value of that condensate. You know, if we've calculated steam at £60 per tonne, that condensate's got a value to us of approximately £15 per tonne. Of course, we want to return and recover as much of it as we possibly can. So the question our client typically asks us is, well, how much condensate am I recovering? We don't know because we don't know what our client is using the steam for. They could be using it for indirect processes or direct processes. But by using the formula on the bottom of the screen, it means that by taking the conductivity of the water in different areas of the boiler house, we can get an understanding for how much condensate is being recovered. Simply put, condensate is already chemically conditioned. It's in a fantastic condition for going back into the boiler. So a chemical understanding of condensate return is every bit as good as mechanical or metered recovery. So a client would then typically ask us, well, how much condensate should I be recovering? Again, we don't know. Another rule of thumb would be if we could recover 85% of our condensate and get it to the boiler house at a temperature of 85 degrees, that'd be a pretty good target to aspire to. But it reminds us that if we can recover as much of the condensate as we possibly can, we're going to have a significant and proven benefit in terms of how we've now optimized our steam system. So, as we mentioned, if we've got all the variables in calculating the cost of steam, the same variables apply with calculating the benefit in increasing the mass of condensate we can now bring back from the various processes around site back to the boiler house. We need to understand that When steam gives up its heat energy and condenses, its useful heat energy goes into the process, and the byproduct that is left behind is going to be a single phase liquid at the same pressure and at the same temperature as the steam, at least until it depressurizes when it moves across the trap. So when that steam, or should I say when the condensate depressurizes as it moves across the trap, that's when we're going to get that phase change in that rapid expansion. And that's when clients are going to be tempted to vent that expansion away to atmosphere in order to reduce the infrastructure cost and in order to minimize any damage that could be imparted by that expansion. The problem is we need to bear in mind that that energy that is being vented away, yes, we're venting the expansion away, but there's a significant amount of heat energy that is also being lost. So if we know the mass of condensate, and if we know the extent at which it's depressurizing, for example, 100 kilograms depressurizing from 7-bar gauge to atmospheric, we then know the mass of condensate that's going to boil off. In other words, the mass or the volume of steam that's produced, but we also know the energy content of that steam. And once we understand that, we can then look at various solutions where we can allow that expansion to take place, but we can capture that energy and potentially divert it back to another process, another heat sink. Now, an excellent heat sink would be perhaps moving away from that atmospherically vented hot well and instead to elevating the pressure and therefore the temperature of the hot water that's held in storage in the boil house. This is what we call a PDA, or a pressurized deaerator. Because it's under pressure, the water's held at a significantly higher temperature. So we don't need to burn as much gas to raise steam again. And because we're not adding as many chemicals to the water, because it's now at a hotter condition, we're not performing as much blowdown. So we've got a further energy saving. And it also means that we've now got an excellent heat sink to recover any of that vented steam to. We're moving closer and closer towards a zero net loss steam system. So a few calculations here. I'm not going to go through these, but it demonstrates that if we've calculated our cost of steam, and if we've calculated the mass of condensate that we can recover from condensate that's previously been going to waste or being lost to atmosphere as it goes up those vents, we can calculate what that payback is going to be. And remember, the payback's not just in terms of reduced steam or gas, it's in terms of the carbon emissions that we are no longer responsible for. So as we've mentioned, steam metering. It's important to meter the steam at the point of generation. It's important to meter the steam at the point of use. So we can put a value on each individual steam using process. So we can understand how much steam is going missing when it's being moved from the boiler to each individual process around site. But we can also use it for diagnostic purposes. For example, if our heat exchanger is calling for more and more steam over a period of weeks, it could be that, well, the steam's wetter and wetter, so there's less energy present within it. Or it could mean that there's a lot of foam that's creating a barrier to heat exchange and slowing the process down. So it's not just for energy observations, it's also for diagnostic purposes as well. So I keep mentioning the term loop. We need to think of a steam system as being a loop for the simple reason that if we know how much steam we're producing, we've got a really good understanding for the mass of condensate that we want to recover. If we're not recovering as much condensate as we may like, that could be down to the fact that we've got failing steam traps that are venting steam away, or we've got flash steam emissions that are arising from other sources, or maybe we've got fractured, damaged valves and pipework components. But it means that if we can monitor that, we can have an understanding of how and where we can engineer those improvements, and we can have a really good understanding of what that financial payback and benefit is likely to be. So coming back to that first slide, as I've mentioned, it could well be that our client is producing 10,000 kilograms of steam per hour today, when in actual fact, they've only got a requirement for 7,000 kilograms of steam. So the first thing that we want to do is ensure that the boiler, it's not working harder than it needs to. We're keeping our gas consumption to an absolute minimum, our cost of steam to a minimum, and our carbon emissions to a minimum. And it's only then that we should then really move forward and explore other ways that we can produce the steam away from natural gas, for example, by electrifying our boilers or by producing steam from some other means, thermal storage or heat pumps, for example. So in next week's presentation, we're really going to move forward and we're going to identify those key areas, those new technologies that we can employ to help us transition from natural gas and retain steam, albeit green and sustainable steam. So I've put on the summary slide, I've really put up those areas that we can hone in on and optimize an existing traditional steam system to really to help sharpen the pencil, to use the analogy that I've used in previous presentations. The first thing that we would do whenever we're looking at our car's economy is ensure that we're using the correct type of fuel and to ensure that we're blowing up the tires. And it's the same with the steam system. We need to ensure that we're employing best practice with the basics to ensure that we're not leaving we're not going out on a winter's day and leaving the front door open, and to ensure that we're turning the hot tap off when we've finished in the bathroom. It is the basics that are going to give us the quick wins today. And in future, once we understand our steam load and once we understand where the efficiencies and inefficiencies of our steam system may be, we can then transition and move forward to look at the next step, which is transitioning towards a newer technology away from natural gas. So for those of you that are still in education, please do take a quick snapshot of the QR read that you can see down in the bottom right hand side of the screen. Our year in industry program and our graduate intake for 2025 is going to commence in the next few days, so you may find that information of use. And hopefully you'll be able to join us for number 8, the last in the series of webinars that we've had diarised over these last few weeks, same time next week. And in that particular presentation, we're really going to drill down and we're going to look at some of those new innovations and new technologies that are currently on the market or at an advanced stage of commercialization that are going to help us to not only retain our existing steam system and steam processes, but are going to help us to generate green steam sustainably in the years to come. So once again, thank you very much for your time and attendance in this evening's presentation. Hopefully you found it of interest. If you are interested in receiving a PDF of the slide deck and an attendance certificate, can I ask that you drop me a message on LinkedIn? I don't have access to the chat function, unfortunately, being a guest presenter, but I can make that information available for you. Please also, if you've enjoyed the series of presentations that we've gone through over these last weeks, please do make a favourable comment on Brian or myself's profile. We'd certainly be grateful of the feedback. I'm not sure if Brian's joined the call. If you have, Brian, probably now's the time to open up your microphone. If not, if there are any other questions that I can help with this evening, then please feel free to type a question, or failing that, feel free to open your microphone and shout something out. I'll be more than happy to address any questions that there may be. So it doesn't look like there's any questions. So on that note, I would like to thank you very much for your time and attendance this evening, and look forward to presenting to you again same time next week. Many thanks.